All right, hey everyone, and welcome to discussion. We're going to be talking about graphs, graph definitions, implementations, and searching. So let's go ahead and jump right in. Okay, so objectives for today are talking about graphs, as I mentioned, the properties of graphs, so cycles, connected graphs, weighted graphs, directed graphs, a lot of different types of graphs, and how we represent graphs with code. Maybe you guys have seen it before, maybe not, okay. Adjacency lists and adjacency matrices. And then we'll talk about graph traversals. And the two main ways to do that are breadth first search and depth first search. And we'll go over some practice questions. So let's talk about graph properties first. So graphs are data structures that consist of a finite set of vertices and edges. And so what that means is, like, a graph, you have like vertices, which are like these 1, 2, 3, 4, 5, and edges, which connect the different nodes or vertices together. And then we represent it instead of, and usually when we talk about like time complexity, so talking about like n, where n is the number of edges or n is the number of vertices. Sometimes we'll refer to them as like v and e, because, or the cardinality of the set of vertices. That's why we use the bars. Those bars are like, if you ever taken, or like in some math classes, they talk about cardinality of sets. So it's a set of all vertices, but the cardinality of that set of all edges, cardinality of that, right? So it's basically the number of vertices and the number of edges. And that's how we refer to them, is number of vertices, number of edges. And sometimes when we talk about time complexity, rather than like saying ON, maybe we'll talk like OV or OV plus E or something like that. So that's just convenient for us, because we're dealing with two things rather than one, right? Okay, so that's kind of an overview of graphs, is that they're just like vertices connected by edges. And yeah, they're unordered, right? Unordered data structure. So in this case, set of vertices is 1, 2, 3, or 5, and the set of edges is 3, 5, because we have an edge between 3 and 5, one between 4 and 5, one between 1 and 5, one between 1 and 4, and one between 1 and 2. That's our set of edges. And so the number of vertices is 5, number of edges is also 5. Okay, so next thing we're talking about is connected graph. So connected graph, well, graph is connected, right, if between any pair of vertices there is a path, right? And so, and then, yeah, so that's what a connected graph is. So in this case, we looked at, or we can look at a connected graph, right? It is connected because between any pair of vertices, if I choose any two vertices in the graph, right, there's going to be an edge between them, right? Or not just one edge, but there's a path between them. So like if I want to go from 2 to 4, I can go from 2 to 1 and then 1 to 4. So there's a way to get from 2 to 4. If I want to get from 1 to 3, like I can just go 1 to 3. So any two, there's a way to get between them. And it's kind of clear to see, right? Like if they're all just like one component, right? There's this one thing, like if there's not just one group completely separated from another group, then it's connected. But if there is one completely separated from the others, then it's not connected. So in the second case, like clearly 2 is not connected because you can't get from 2 to 1, 4, or 3. So that's not connected. And these are both undirected graph. We'll talk about undirected in a minute. But it's a connected graph if all vertices are, right? Okay. All right. So directed versus undirected. So a directed graph has directions associated with its edges. So you have to follow the direction of an edge if using it in a path. An undirected edge or an undirected graph only has undirected edges. So there are no arrows, basically. Like if you have arrows that tell you the direction you're going in, then that's directed. But if it's undirected, then basically it's almost like it's bidirectional. It doesn't matter which way you go. So in the second example, directed one, there's an edge between 4 and 1, but not really. It's only an edge between 1 and 4, right? You can only go from 1 to 4, right? Because direction matters. But in the first one, you can go from 4 to 1 or from 1 to 4. So having no direction is almost like being able to go either direction. Right? But between 4 and 1, that's like in the second one, and directed one, that's not the case. Like because there's clearly an arrow that like points from 1 to 4. You can't go in the opposite direction. Right? So that's the difference between undirected and directed. Is directed, their directions, and undirected, their no direction. It doesn't matter. Okay. So what is a path in a graph? Well, a path, and we mentioned path like in the previous 2 slides, but now like saying what it is, it's some sequence of vertices with the property that each vertex in the sequence is adjacent to the vertex next to it. So in this case, possible paths, for example. So 3 to 2 to 1 to 4, that's a path. So let me draw this. Let me draw over. This is a path, right? And that's how we represent the path, right? And 1 to 2, it's also a path. 1, 2, 3, 1, 4. I mean, yeah, like you do visit something more than once, but it's still a path. Right. And a simple path is a path that doesn't repeat vertices. So, for example, maybe you can think to yourself, okay, which of these are simple paths? And okay, I guess just looking at it, right? Looking at these three, it's kind of clear that this one's a simple path, this one is too, but this one's not a simple path because 1, 2, 3, 1, we've already visited 1. So it's not a simple path. But in general, just a path goes through the graph, right? It visits the vertices. Basically just visiting some vertex that's connected by an edge to the vertex you're currently in. And a simple path just doesn't visit any vertex more than once. So okay, what about graph cycle? So a cycle in a graph is a simple path. So that's some sequence of vertices which are all connected by edges to one another, in which you never visit a vertex more than once. And it's a cycle if you have that path and the first and last vertices are the same. So that's another way we can do it. That's how we can define a cycle. But if you think about what a cycle is like in general, right? A cycle, like you start somewhere and you go somewhere else, right? It's like a loop. That's exactly what we have with graph cycles, right? Is this condition ensures that there is some path which you start at one place and go back to where you started. It means there must be like some sort of, it's a cycle in the graph, right? So like for example, and an acyclic graph just has no cycles. So the first one, right, is acyclic because if I start at 4, like the only way I can go back to 4 is if I visit 1 again, right? And then it's not a simple path, right? So like the only way to get back to 4 after leaving 4 is to go back through 1. But that means I can never get back to 4 again without having to visit 1. So it won't be a simple path, which the first and last place are the same. And the same thing is true with 1, right? I can't visit 1 again without visiting 3 again, 4 again, or 2 again, right? And same thing with 2 and 3. So it's acyclic because, I mean, just looking at it, right? There's no cycle. Usually with a cycle, you'll see, okay, like it's just, it forms a cycle. Like, let's look at the last one. Here, this is, you can kind of see as a cycle, right? Because there, 3 of them, they form a cycle. These 3 form a cycle. This is why this graph is cyclic, because you can go 4, 1, 3, 4. And I visited 4 twice, I visited 1 twice, or 3 twice. So usually they're kind of easy to see. But interestingly, if you add directions to it, it's not necessarily direct, it's not necessarily cyclic, because this case, right, that's not the case. It's not cyclic because there are directions, right? So I can't go 1, 4, 3, 1, for example, because that would be going against the way this one goes and against the way the other 1 to 3 goes. So if we just look at it, right, 1 to 4, okay, and then I can't go any further. 1 to 2, I can't go any further. 1 to 3 to 4, then I can't go any further. So there's no way to make a cycle. So that's why this is acyclic. There's no cycle, acyclic, no cycle. This one, there's a cycle, right? That's why it's cyclic. Okay, so that makes sense. And oh yeah, and trees, which we talked about in this class, are a type of acyclic graph. And they're acyclic. Well, there are a number of ways to show the acyclic, but I guess based on what we talked about already, right? They're acyclic because if you want to get back to where you started, right? If we were to like draw out the tree, if you want to like get some sort of cycle, so you want to go from here, let's say from some root, let's say back to itself. Well, the only way to do that is, the only way to get to that root, let's say in a binary tree, is to either visit this one again or get to this one. But if we're in the right subtree, right, we can't go back up and visit this one again. So just kind of clearly, or we can't get all the way over here because we're in the right subtree. And if we're in this one, we have to visit this one again. So just kind of clearly, you can maybe see why it's acyclic. But in general, yeah, trees are always acyclic. Okay. And we'll talk about maybe extensions of things we already know about for trees and graphs in a minute. Okay, so the next thing is weighted graphs. So a weighted graph is a graph which has weights associated with it. So far all we've seen are unweighted graphs, and unweighted graphs just have no weights, right? There's no edge weights, but weighted graphs have weights on their edges. So let's look at this example, right? Here, this edge has a weight associated with it. It's -5. This edge has a weight of 10. This has a weight of 2. This has a weight of 4. And these don't have weights. Maybe you could say the weight is just all 1, but in general, we just say it's unweighted. Okay. So that's the difference between weighted and unweighted. Is weighted has values on their edges, which make them so-called weighted, right? And unweighted, there's no values associated with each edge. Each edge is the same. All right. So let's do a poll question. So you can pause and try and answer. Which of the following is true of the below graph? Okay, so we've been paused. So let's go through them. So first of all, we need to decide, is it acyclic? So does there exist some cycle in this graph among some of the edges or some of the vertices, right? Is there a path, a simple path that starts and ends with the same vertex? Well, at 2, no, and there's not. And at 4, there's also not, but at 1, there actually is. And we can look at what that path would be. It's 1 to 5, 5 to 3, and 3 to 1. And so as a result, it's not acyclic because we found the cycle. Okay. Now next, we're going to go ahead and look at the next one, which is it connected? Well, it's not connected, right? Because this 6 is off on its own. So it's not connected because 6 isn't connected to the rest of the graph. Is it weighted? Do the edges have weights on them? They do, right? Between any two, there's a vertices, there's an edge, and well, where there's an edge, the edge has some value associated with it. So it's weighted, yes. And is it directed? It's not directed because the edges don't have direction to them. They're all undirected edges. So there's no arrows is how we can kind of see it. So the only one of these which it is true of this graph is that it's a weighted graph. And we look at the answers, that's exactly what we see. Right. Okay, hopefully that makes sense too. Okay, I'm moving on. So now graph representations. This is how we kind of represent graphs in code. So the first way we can do it is with adjacency lists. So this is good for sparse graphs where the number of edges is a lot less than the number of vertices squared, right? Because the most edges we can possibly have in a graph is of order of v squared, right? Like for example, we would have, and the reason why this is true, right, is like, let's say we had an undirected graph. This is just an aside we quickly will talk about. But let's say we have 4, right? The most we can have for the first, let's start with the first one, right? First, we choose this one as our first node. So label it 1, well, we'll label them all, 2, 3, and 4. So if we choose the first one first, how many different options do we have for choosing what it's connected to? Well, 3, right? And for 2, well, it's already connected to 1, but now we have, it can be connected to 4 and 3 can be connected to 4. So how many possible edges would there be? Well, it would be n-1 plus n-2 for the second plus ... right? And maybe you can see where it's going, right? All the way down to 1. And what is the sum? Well, the sum is of order n squared, where n in this case was just v. So the most edges we can have in a graph is of order v squared. But maybe we know our graph doesn't have very many edges, right? Maybe it's a sparse graph, is what we call it. It doesn't have very many edges. And if that's the case, then maybe it wouldn't make sense to store like information about every edge, whether it exists or not, or what the value is, right? If there aren't necessarily edges at between each vertex, edge pair of vertices. So what we can do is we can make a list of lists of nodes. So every combination of the outer list and inner list is an edge. So representing this graph, 1 to 2, if there's an edge from 1 to 2, right, then in our list, right, what we would do is we would have, okay, for 1, we'd say, okay, 1 connects to 2 and 1 connects to 5. So in 1's list, there's a 2 and there's a 5. And in 2's list, well, what's it connected to? 1, 5, and 4, and 3. So we would have 1 in 2's list, 5 in 2's list, 3 in 2's list, and 4 in 2's list, right? What about 3? Well, in 3's list, we have 2, it's connected to 2, and it's connected to 4, right? Which we can see here, 2 and 4. And the next one, 4 is connected to 3, 2, and 5. So we see those, and 5 is connected to 4, 2, 1, or 4, 1, 2. So that's kind of how we represent it, right? for each vertex, we just keep track of like what its neighbors are basically, like what is it connected to? And then we just make that into a list, right? So the list is all the things that this node is connected to. But maybe for something that isn't a sparse graph, there's another way to represent it, which we'll talk about. Okay, well, first we're gonna look at this animation. So 1 is connected to 2 and 5, or 1 is connected to 5 there, and so on, right? It's the same. Okay, and okay, first adjacency list operations. So checking adjacent pairs. So is 1 adjacent to 5? How much time would that take, right? You have to traverse 1's list or 5's list. If it's undirected, you can check is 1 adjacent to 5. And so you have to traverse the entirety of the list, right, for 1. You have to check all the ones that 1's connected to see if it's connected to 5, right? Because maybe, yeah, you don't know, there's not necessarily some ordering to it. So you have to traverse all of 1's list or 5's list. And so the number of things you're gonna have to check is the out degree of 1, right? It's the number of things that are connected to 1. So that's our time complexity. So getting neighbors, what nodes are 1 adjacent to, you have to traverse all of 1's list, right? And that's why it's similar to adjacent pairs, it's still out degree. And out degree refers to the number of ends coming out of the vertex. And the reason why we specify that is because if it's directed, that does matter, right? Because like there, then 1 is connected to 2, but 2 may not be connected to 1. So, or 2 is not connected to 1 in this case. So we wouldn't have, if it were directed like this, we wouldn't have 1 and 2's adjacency list, because you can't go from 2 to 1, but you can go from 1 to 2. So that's why this remains. That's why we specify out degree. But for undirected, it really doesn't matter. It's the same both ways. And yeah, so out degree. Okay. So maybe, as I said before, yeah, we can represent it a different way. And so we have an adjacency matrix representation. And so this is really good for dense graphs where the number of edges begins to approach the order of the number of vertices squared. So if it's really dense, like there are a lot of edges, then representing it as an adjacency matrix makes sense. And in general, representing things as adjacency matrices makes things a lot easier to write code for. Well, at least I think so. But okay, well, I guess you'll see, but I think most people I've talked to would agree on that. And yeah, adjacency matrices are good for dense graphs, as we have said, and they represent all possible edges. So basically, whether there's an edge or not, this is why it's good for dense graphs, maybe not so good for sparse graphs, is because even if there's no edges, or even if there are not very many edges, right, we're gonna represent every single edge. And if there's no edge there, we're just gonna say, okay, well, it's 0 because there's no edge. So we just say, okay, 0. So it's gonna look something like this. So we have basically the number of vertices is the number of columns and the number of rows. And if there's an edge between like column I and row J, well, I guess it'd be better if I did that, right? Row I and column J, right? If there's some edge between them, then we put a 1. So if there's an edge between 1 and 2, well, 1 and 2, we put a 1 there. And there is, right? But there's no edge between 1 and 4. So if we go to row 1, column 4, we should see a 0, and we do. That's what I represent it. So for every single edge, like whether it exists or not, any edge that could exist, basically any pair of vertices in the entire graph, we're going to have some form of value or some sort of data. It's going to be, if unweighted, that's going to be a 1 if it exists and 0 if it doesn't exist. So like from 1 to 5, right, we're going to have a 1 there. But then also, if we look at the columns from, if we look at, okay, well, yeah, so if we look from 1 to 5, right, so 1 to 5, we're expecting to see something. But also from 5 to 1, we're expecting to see something. Now remember, if it's directed, that may not be true because it only goes in one direction. But for undirected, it should be symmetric about this axis. Because if I'm connected to this person, then this person has to connect to me because it's undirected. So that's what I should see. And okay, so that's what we have for this. But also if we look here, like 1, right, is connected to 5, and 1 is connected to 5 and 5. So if we go either by the columns or by the rows for an undirected graph, it should be the same. right? But the main takeaway is like, if 5 is connected to 1, then we have row 5, column 1 has a 1. And if they're not connected, you put a 0. Like row 5, column 3 is a 0 because they're not. Okay, so I realized that was a lot. Hopefully you kind of followed that. So we kind of think of, okay, how does this perform? How does it work exactly, right? And okay, first we can kind of see, right, 2, 5, that's why I have 1 there. Okay, but we usually use arrays to represent this, right? We use like a 2D array because it's just a matrix. So how bad is checking adjacent pairs then? Like, is 1 adjacent to 5? How much times is that? Actually, not a lot at all, because if we're storing it just in arrays, it's random access, right? So it's just O1 because we just make a check, right? Basically check 1, 5 row, right? Row 1, column 5. Let's make a check and we're done. We're not getting neighbors. So if we want to check the neighbors that 1's adjacent to, we have to go through all of the things in that row or the column. And no matter how many things that 1's connected to, we have how many columns or how many rows? V, because we have to check whether it's connected to everything. So O of V for traversing a more column. But checking is only O1, but traversing is O of V. So there are trade-offs, right, between this and adjacency lists, as you can imagine. Like this one takes more time to traverse, less time to access. This one's easier to code, but that one takes less storage in general, right? So things to keep in mind. Whole question number 2. So what's the time complexity of checking what a vertex is adjacent to in an adjacency matrix representation? You can pause and try and answer. Okay, now we're going to the answer. Well, we kind of just mentioned this, right? If we want to know what a vertex is connected to, that means you have to check in its entire row, right? And for anything there's a 1, then like for unweighted, anything there's a 1 there, it means that they're connected. Anything that there's a 0 there, it means they're not connected. But to know, we actually have to check them all. So that's O of V. Right? Yeah, O of V because it traverses the entire row and check all adjacent vertices. Okay. So next poll questions. Given this following adjacency matrix, what's the path from node A to node I? And yeah, the hint is to follow the answer choices in the matrix. So you can pause and try and answer it. Okay, so now I'll try and go up. So from A is, what is the path from, what is a path from node A? So let's try A to F to I. So first we're going to check we're going to check the path from A to F. Is there a path from A to F? There's not, so we can't even do this. Is there an edge between A and C? Yes. Is there a path between, now we go to C to G. Is there a path between, or is there an edge between C and G? There is. Now, is there an edge between G and I? G, I. There's not. So this is also not right. What about the next one? A to B to E to I. Does that work? Well, we start at A, we check B. Okay. Now B, we're going to check for E. And so far, so good. Now we check, is there an edge between E and I? And there is. So there is one between A and B. There is one between B and E. And there is one from E to I. So this is a path from A to I. That's kind of how you go about it. You check one by one, right? So it's the third one. And we can kind of see that this is what the graph actually looks like. So we could also just draw the entire graph in this manner. We can, based on this adjacency matrix, we can actually draw the graph. And this is what it would look like. And clearly we can see now ABEI is a path from A to I. Okay, so now we're talking about graph traversals. So these are kind of important, just in general. Graph traversals are like key to graphs, but a couple of things about them. So like for any of you who may be doing technical interviews and things like that in the future, it's a big topic. It's kind of important for those. Another thing is like, it's kind of maybe kind of scary at first, these, but graph traversals are just an extension of tree traversals. Like everything we did tree traversals in the past is just what a graph traversal is. it's just an extension because a tree is just a kind of graph. If you remember, we had for a tree, we had like level order traversal, and that's just breadth first search in a graph. And it's pretty much implemented the same way for a graph. And for the other traversal we had, like left node right, and then like post order pre order in order, those are all depth first searches. That's a kind of tree of graph traversal. And it's just an extension of those. That's all the graph traversals are. It's just an extension of the ones we've already seen for trees. Okay, so graph traversals. So they're classified in order in which the vertices are visited. So there's some traversal algorithms. So there's ad hocs, you can randomly visit each vertex. I mean, that's like, probably not the one you want to use in most cases, but maybe in some cases, I don't know. And the other two are depth first and breadth first search, which I mentioned a moment ago, and just kind of similar to they're just extensions of the ones we've seen for trees. The time complexity of a graph traversal is b plus e. Maybe you can think about it and realize why. And the reason why is like even just looking at this graph, let's use this as an example. If you want to visit all of the vertices, right? Well, there are v vertices, but to go from one to another, right, to actually make a path, you have to visit all the edges along that path. So in total, we're gonna have to visit every edge. We're gonna have to visit every vertex. So O of v plus. Now, in general, right, E is larger than V. Not always, but usually so. Okay, it's usually just, usually O of E kind of dominates the term, but we call it O of E plus, because that's what it is. Okay. So if you're ever confused about this, graph traversal and graph search mean the same thing. Graph search is just a traversal of indices until you find something. Okay, so depth first search. So depth first search is like in order, post order, and pre-order. Basically, we just keep going in one direction until we can't go any further. And then we start backtracking back to where we go back to where we last made a decision. And then we're like, okay, well, that decision, maybe I didn't reach what I wanted to. So, okay, I go as far as I can now in this direction, right? It's kind of like with trees where we would go all the way in this direction. And then we're like, oh, okay, that didn't work. So we go back up and then we go all the way in this direction. Like, okay, we go all the way this way now. And okay, that didn't work. So we go all the way this way. And okay, we go back up, we go back up. Same idea for depth first search. This is just an extension of that. So at a given vertex, you visit all the children before visiting siblings. So in this, actually, I'm not going to draw my own, this one right here. In this graph, right, maybe we start at S. So at S, what we're going to do is we're going to visit everything in this, with the tree, right, it would be left subtree. But for a graph, we're going to visit everything on like that starts with this edge, right? All the paths start with this edge first. So we go to A. Then from A, we go to D. And from D, we go to G. And now G, we're going to visit E first. And then from E, we're going to visit B. And we're going to see, okay, we already seen S, so this edge we don't need to go along. And then we're going to be like, okay, G to F, F to C. Okay, we don't need this one either, right? But then we're going to go, okay, where was the last time we made a decision? Well, we made a decision to F. There's only one decision. Only one at G, only one at D, only one at A. Only one at, well, we went along S. Now we're going to go, now we finished everything that went to A. So now we're going to try everything goes to B. Oh, we've already seen B. We don't need to keep going. And then we're like, oh, okay, let's go to our next choice, which is C. Oh, we've already seen C. So we're done. But maybe what you kind of saw here with DFS is it's just like the traversals for trees. You keep going one direction until you can't go any further, and then you go back up, and then you try the next direction. So examples of when to use these would be solving mazes, topological sort, which we'll talk about next week, planarity testing. I think it's for planes. I don't know. I'm not entirely sure. But the main thing I usually think of when I think of depth first search is solving a maze. Because I don't know, when I think of a maze, right? Like if you're trying to get out of a maze, like that's a really bad maze, but whatever. Maybe this is the path through the maze. Maybe this is a dead end. Right? This one dead end. No good. Then maybe I go along this direction. I keep going. Oh, I hit a dead end. So I go back to where I went to, and then I keep going in one direction as far as I can. So like when you're drawing a maze, like this is probably kind of what you use step for search. Where like the nodes are the decision points and the edges are like the paths between decision points that we have to choose away. So I don't know, depth first search. Okay, so how do we write a depth first search? Like what does it usually involve? Well, it's the same as a traversal, like same exact thing. Use a stack. Use a stack. Time complexes O of B plus C. Use the number of vertices, use the number of edges in the graph, because you visit every vertex once, and then you visit every edge once as well. So yeah, it's like almost exactly the same. So you start with your graph, you start with your vertex, because the vertex where the search starts. You have an empty stack at the beginning. For each vertex you say at first I haven't visited it. But then at the very beginning, you're going to say, okay, onto the stack, you're going to push the starting vertex. And again, just like with a stack with depth first search, while S is not empty, you're going to get the top of the stack, right? If you have not visited it, then visited you is true, right? So if you haven't visited before, you mark it as true, you mark it as visited. And if you haven't visited before, you visit all its neighbors. But for each of its neighbors, you're going to put them on the stack. And that way you visit the first one and do everything along that path of the first one before you visit the second one, because you're using a stack. So this behaves just like how it would for a tree. Like the code is almost exactly the same. So that's depth first search. Okay. Hopefully that made sense. And now we're going to move on a little bit. So now we're talking about breadth first search. And breadth first search is just like level order traverse. At a given index or a given vertex, you visit all the siblings before you visit their children. So you explore all the neighbors the same depth away before exploring deeper. So, okay, yeah, it's good for finding the shortest path in a graph. That's generally how we solve it, is with breadth first search. We also have the tree from Metzland, German city, starting from Frankfurt. So the way we would do this, right, it, like, even looking at this, right, like this one on the right is just a tree, right? Okay, maybe the one on the left looks different, but I mean, essentially that's all it is, right? Because we go, okay. Yeah, and the way we would actually do the breadth first search is we'd say, okay, we started Frankfurt. And now we're going to go to its neighbors first, right? So this one, and then we're going to visit this neighbor, and then we're going to visit this neighbor. And then once we're done with those three, we go, okay, let's visit this guy. And then let's visit this guy. Let's visit this guy. And let's also visit this guy, actually. So basically, at each level or each time, you visit all of its neighbors which you haven't visited yet. So it's just like with a level order traversal. You visit everything at a certain level or distance away from your start node. So if your start node is Frankfurt, you visit every node distance 1 away from Frankfurt first. And the next time through, you visit everything distance 2 away, which is the same as what we're doing with trees, because with trees, we're visiting everything level 1, everything level 2, level 3. Now it's just distance 1 from your root, distance 2 from your root. And it's the same thing, right? And in a tree, like even that was distance 1 from your root, because anything of level 2 is still like, anything like level 2 maybe is like distance 1 away from your root, and level 3 is distance 2 away from your root. So it's the same algorithm. It's just on a graph, right? So instead of like just a tree, so it's just an extension, but it's the same algorithm. So for breadth first search, we use a queue, just like we with level order traversal. Time complexity is again, see, these are the number of vertices and these are the number of edges in the graph. So you visit each vertex one time, visit each edge one time. That's why we get that time complexity. So again, we start with a graph. We start with the start node. We have a queue, and we start with an empty. Start with an empty queue. And then for each vertex queue, you set visited to false, like you haven't visited anything yet at the beginning. And then you mark S as visited and you push it onto the queue. And while your queue is not empty, you dequeue, and then for each neighbor, you put it on the queue and then say visited is true. So as you can see, it's like the exact same code as you would have used for a tree because it's the same thing. Just on a graph instead of a tree, but trees are graphs, so yeah. Okay, but that hopefully kind of goes over breadth first search and depth first search. And yeah, maybe a quick drawing will help. I don't know if it's still confusing. So let's say this is our graph, right? And so what we would do is, let's say we're starting here. Then in a breadth first search, in the first pass, we'd visit this guy and this guy, because they're both distance 1 away from where we start. And then in the next pass, actually, wait, let's just add another one, just because I don't know. The next one, this guy is distance 2 away, right? So we visit him and him, right? Because these ones were distance 1 away from this one and this one. And the next one, next pass, we're going to visit this one. But the interesting thing is that as you're going through it, right, each time as we went through, we visited all things distance 1 away. And the next time through, we went and visited all things 2 away. Next time through, we visit all things 3 away. And the interesting about that is, like, let's say that we wanted to find, I don't know, like the shortest path. Actually, I'm not sure. We might actually go with it. Okay, whatever. If we wanted to find the shortest path from our start to an end, maybe kind of see where that would go. But okay, I'm not going to get into that yet, because I think we might go over it in a minute. But let's see what a depth first search would do for this graph. Well, we'd still start in the same place. But then we would, let's say, go here. Let's say we just go to the bottom one. I would just favor going to the bottom one if we can. So we visit this one first, then we visit this one, then we visit this one. And now this one we can't visit anything else. So go back to this guy. And we visit this one. And then from this one, we're like, okay, well, let's visit this one. And now we go back to this one here. Like, oh, okay, well, we've actually already visited this guy, so we don't go backwards. So now we go back to where we were before we visited this one, which is here. Like, okay, well, we have to backtrack again. This one's like, okay, nothing else to visit. Let's backtrack again. We're back to our start. And our start, now we're going to choose the other direction. Oh, we've already visited, so we're done. So this is how depth first search works. But breadth first search, as we just went over, visits distance away each time. Hopefully that's clear. Full question number 4. What do you use for BFS? What do you use for DFS? BFS is breadth first, DFS is depth first. So I'm going to try and answer. Pause it if you want. I'll go over it. Okay. So the answer is BFS use a queue and DFS use a stack. Okay. So problem solving using choices. Now we're going to go over some problems. So flood fill in a bucket fill tool of a paint program to fill connected similarly colored areas with different color. So write an algorithm that performs the flood fill program using a breadth first traversal. So the way we can maybe do this, right, is each pixel wants to fill all of the same color pixels around it before we expand. So this is behavior breadth first search, right? You don't color pixels that were a different color, the original start color. So if it's the original start color, then we fill it in. But if it's not, then we don't. Right, and we keep going one away. That's what you're seeing here, right? It's filling in, going further and further from our source. Okay, so yeah, this is why I didn't want to go over the answer to that question a minute ago, is exactly because we're going over it now, and I wanted you to have a chance to do it yourself. So given the edges of an undirected, unweighted graph and 2 vertices u and v in the graph, write an algorithm that computes the minimum number of edges between vertices u and v. And maybe you can use one of the things we've learned today. And assumptions you can make, there will be at least one path from u to v, and we have a set of edges, set of vertices. Well, a set of edges, right? And then we have the vertices. Basically, what this tells us is that we're getting, well, it could be an adjacency matrix or adjacency list, but let's just assume, for simplicity, that we're given an adjacency matrix. And this is our start vertex, this is our end vertex. So how might we do this? Well, in this case, it's clearly 2. But in general, how? So maybe you can try and write a program for that. given an adjacency matrix and a start node and end. Okay, you can pause and think and we work on it. Now we can go over it. Okay, so let's just talk about it, right? So the main thing is that we're given a start vertex, right? And we know that we have one, U, and then we know we have a path to V. But okay, maybe we can start thinking of how do we get a path in a graph? Like, how do we make sure that we know there's a path? Or like, how do we find the path? Well, so far today, we've actually talked about a couple ways to do that, right? And those are graph traversals, right? And so there are two main types of traversals we've talked about. There's BFS and DFS. And I'm just going to write those here. And so what do we remember about this? Well, DFS keeps going as far as it can until it can't go any further. And BFS just goes distance one way the first time, distance two way the second time, distance three way and third time, and so on. In this case, we're trying to find the minimum distance path. Well, the good thing about BFS is that it allows us each time, it's going to find everything in this distance one way, everything in this distance two way. And DFS is also good because it allows us to get an entire path. Which one do you think would apply better here? Maybe you think about it. The answer is actually BFS. And the reason why BFS is good here is because if we're able to find all the vertices of distance one away from U, right? Let's say we start at U, find all of them one distance one away from U. If one of them is V, then we're done. And we say, okay, the answer is 1. Then we go ahead and we say, okay, now let's find all the ones distance 2 away from U. And if V is one of those, well, it couldn't have been distance 1 away because we would have already found it. So if we find it now, distance 2 away, then we're like, oh, 2 is the closest or shortest path to it. So the answer is 2. And then we'd be done. But if it's neither of those, then maybe it's going to the third, and so on. And so at each point, right, if we find V, we know the shortest path is from U to V, is the iteration we're at. And so that's really nice. And that's why BFS is so nice for this problem. It's because to find the number of edges between U and V, it's just a BFS, and we just terminate as soon as we see V. So basically, we just run a BFS, right? Is the main idea. We run the BFS, and at each index or at each iteration, we just keep track of what distance away we are from our root right now, or our source, or the start, or basically how far we are from U. And as soon as we see V, we break out of our loop and we say, okay, whatever iteration we're on, that's the distance, that's the number of edges. So in this case, let's try even doing that. So U. So far at U, our Q is empty, right? Nothing in our Q except, I guess we have U at the beginning, right? And our distance, let's keep track. This is our Q. Let's also keep track of our distance. Distance is at the beginning, 0. Well, next thing we're going to do is we're actually going to set, okay, well, U is not V. So we're going to set distance to 1. And we're going to remove U from our Q. Remove U from our Q. And we're going to put all the things distance 1 away. So we're going to put X, we're going to put P, we're going to put D. And none of these are V. So none of them are V. So then we have to check everything distance 2 away. So we're going to update our distance to 2. And when we do that, well, the first thing we're going to do is we're going to remove X. And at the end of this, right, and we have to do that, we're going to basically find all the neighbors 3 times, right? Just like with level or traversal, where we have to say, okay, how many things are there at this level we still need to go through? Well, it's the size of the queue at the end of the previous iteration, which at this point was 3. So we're going to remove X, and we're going to replace X. What are we going to replace it with? Well, whatever its children were. It doesn't have children, or its neighbors. It doesn't have neighbors that we haven't already visited, right? So, okay. Well, we also need to keep track of what we visited so far. That was the other thing. Sorry, forgot to do that. So we visited U so far. Now we visited X. And okay, we've also visited, we can also say we visited P and D. Because they're in our queue. So we visited UX, P and D. Well, X, there's nothing there. So we removed X. Now the next thing we're gonna remove is P. When we see P, right, we're gonna say, okay, it's connected to C. So now we add C. So we add C to here. That's something we've seen now. And now the next thing we have to remove is D. So we're gonna remove D. And what are we gonna add onto our Q? Well, whatever is connected to D. Oh, I originally forgot W, didn't I? Oh my goodness. No one told me? No, but okay. Well, it wasn't just, then okay, we'll just add that at the end. D, W, C. Okay, well, we just removed W, D, right? And now we put N, right? Because N was a neighbor of D. And okay, and now we say, okay, we visited N, we're seeing N. The next one we're gonna see is, okay, we're gonna see W. Now W, its neighbors are M. We already have N here, so we don't need to add it again. And we're gonna also put V. We visited V. And notice, because we visited V and distance is 2, we're done, because now we know there's a path from U to V of distance 2. So we return 2. And that's it. Basically, it's just a BFS. And we just break out of the BFS, we break out of the iterations if we find what we're looking for. Let's see the code for it. Exactly what we talked about. Create a queue and put U into it. Mark U as visited. While the queue is not empty, go through every edge in the queue and increment the weight of every bird. Well, the vertices edges in the distance. Right? Okay, so this is a slightly, I mean, this is slightly different way of going about it because they're actually keeping track of the weight on the vertices, but both ways will kind of work. It's essentially the same solution though. It's just that they're keeping track of the vertices along with the weights, if that makes sense. Rather than just keeping track of the distance at each iteration. But both solutions would work. And as you notice, it's just a BFS, just like level or traversal of a tree. And yeah, it just checks each time. Okay, well, it doesn't even bother checking because this one doesn't break out of the loop. It just says, okay, what's the distance away? So this one just keeps track of what the distance is from every edge or every vertex to every other vertex. So this one keeps track of, it basically finds distance in every path. Ours stopped at some point, but there just keeps track of all of them, which is also fine. But that's the only distinction. Otherwise, it's exactly the same. And yeah, as you can notice, right, this one just says, okay, if there is a path from, if there is an edge, right, from like X to I, then okay, the distance will be distance of X plus 1. Like if we haven't seen it before, then that path must be distance 1 more. Okay. But same idea. So hopefully this made sense. So moving on to this problem. This problem is kind of difficult. And this is kind of similar to things that I know some of my friends have seen in interviews. So it's a good question, I think, because it's kind of tricky when you first see it. But then you understand it, and it's a really good problem to know how to do. So if you're given it an m by n 2D binary grid, which represents a map of ones, which are land, zeros, which are water, turn the number of islands. And an island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically only, not horizontally, horizontally or vertically. I can assume all four edges are surrounded by water. So basically, what this is telling us is that we want to know basically like how many islands are, so how many like groups of ones. So maybe you can kind of think about this problem. If you need to talk about it some more, we'll talk about it in a minute. But if you want to pause, try and work on this problem, maybe you have an idea, go ahead and try it. Then we'll talk. Okay, so you can pause. Okay, so if you've unpaused, then let's talk a little more. In this case, we already see this example, the output is 3. And the reason why it's 3 is because this little component here, this component here, this component here, if you're not connecting to anything else, right, are, well, they're all islands, right? There's no, or they're all land, right? And so they're all islands themselves, and there's no water in between them. right? Or that forces them to not be. So, okay, so maybe what we can think about is, what is special about these, and how can we turn this into something we talked about today? Well, we can already kind of see how this is kind of like a graph, right? It's kind of like a graph in that, okay, maybe each one is a node, and the edges are what it's connected to vertically and horizontally. So that's a nice trick to have, right? So this one, for example, let's just say, okay, it's a node, it has value 1, and it's connected to only 4 things, and they all have value 0, right? That's kind of how we're going to think about this. That's how we're going to think about this graph. So we're going to think about this as this thing as a graph where the edges, there's an edge between anything you're connected to horizontally, anything you're connected to vertically. So this guy is connected to this guy, like this, like these are all connected to each other. This one, these are connected. But maybe it's not so clear still how to solve this problem, right? I mean, that's a nice start. But okay, this kind of problem, though, is kind of something you might see a lot. So it's good to have a good idea of like how we can approach this. But let's think a little more. Maybe something's clear to you now, but maybe it's not, and that's okay. So, okay. So how do we continue with this problem? How do we solve it? Well, these ones here, right? They're all one big component, right? We're basically trying to find the number of, another way of formulating this problem is the number of components of one such that none of them border another one. So basically we want to find all the groups of ones such that all the nodes that border them are zeros. So basically, one way we could think about this, right, is we want to find just all the groups, right? So how can we possibly make a group? Like maybe we want to use, I mean, it's maybe not clear how to use a traversal yet. Maybe it is, and that's great. But what kind of traversal maybe could we use? Well, how about this one? Let's just start at this one, right? What we can try and do is we can try and find all of the ones which are connected to this one, right? Because in our formulation of the problem, right, it's an island, like another land is part of the same island. If there is some, if there are ones connecting it in some way, horizontally or vertically. And what does that mean? Well, that means that this, like any other random one in the graph, is on the same island as this one if there's a path from this one to the other one. Maybe you can think about that. Maybe that's a little confusing, but think about that for a minute. Maybe it'll become clear. Basically, yeah, this, like any path from one to another one, if there is such a path, if there's a path, but that path only uses other ones to get there, right? Then they must be part of the same island. Because like if I'm a neighbor horizontally or vertically of another island or another land, right? Which is one, right? Then we're part of the same island. And if neither of us are connected to another land, then that's it. That's the end of the island. But if I'm connected to another land, then he's part of the same island as the other guy because I'm connecting them. Or if he's connected to a land, but I'm not connected to another land besides him, then like all three of us make up an island and we keep going, right? And that's how we decide there's an island. So that's how we're going to solve this problem. So we're going to say, okay, start at this one and keep going in this direction and then keep going in the other direction. So go all the way right, all the way left, all the way down, all the way up until we hit no land in that direction. Because if we do that, that's basically getting all the area surrounded completely by water. So basically, we're going to keep going. We're going to find all of the different parts which connected by some land until there's no more land connected because that's the end of the island. And once we've done that, then that's the end of that island. So now we find the next one in the graph. And the next one in the graph is where another island has to start. So maybe you can kind of see what traversal we're going to use. We'll keep going in one direction, right? That's a DFS. So basically, we do a DFS at a land until we've hit all the lands in our component. And then once we've exhausted all of those, we find the next land. how could we possibly, maybe we can start talking about implementation details. Maybe there's a way to keep track of that, right? The way we keep track of that is like we find everything in the island. That's fine, right? That we can do with the DFS. And once we've done that, we mark them all back to 0. So it's like, okay, now we increment the number of islands. We increment the number of islands, number 1 island. We put them all at 0. That way, in the future, we can just treat them as water, and we don't have to worry about like double counting, which we shouldn't have to do anyway. But like it makes things easier for us, and we know exactly where to start the next time. And now the next one, okay, well now we find another one. We check everything it's connected to. It's not connected to anything. So we're done. I mean, we already did DFS on it. Now we're at 2. Find the next one. Well, we set this one to 0. Find the next one. Oh, it's here. Check everything connected to it. Oh, count it to 3. It's just these 2. And then we set them to 0. And there are no more ones in the graph. That's what we get 3. So we just do a DFS where all of the start nodes are where 1s are, because we don't have to worry about double counting, right? Because we set all the 1s from other components back to 0. I know that was kind of convoluted, but hopefully it makes sense. So here's the solution using DFS. We're counting the number of islands. So we use the DFS, loop over all the indices of the 2D array. For each index with value 1, increase the number of islands and call the DFS function. So anytime we find a 1, we call DFS starting from there, and it's going to recursively make the non-zero vertical and horizontal neighbors 0, so we don't count them again. And it's going to just like basically find everything in that connected component, set them to 0, right? And then when we're done with it, right, then okay, that means we've gotten everything in that island, so we go on to the next island. And because if it wasn't connected that way, it's not connected here, right? Like if we're done with that island, then and there's nothing from that island that could be in a different island, because they're islands, they're not connected to each other, right? Otherwise, there would all be one island. So okay. So anyway, I don't know. Yeah. Why is Greenland the biggest island? I mean, like North America is like a bigger island. But okay, that's besides the point. Just I thought I had it just now. But okay. Anyway, so here we do a DFS, right? And as we noticed before, right? Well, the first thing is our DFS, right? The reason why we're doing this check is to make sure we don't go out of bounds, and that's important, because if we go out of bounds, right, we have an error. But otherwise, notice that like we're just using the stack. So this is just basically like our DFS, our traversals with a tree. And here we go, num islands, we just loop over all of the rows and columns. If there's a 1 there, right, it hasn't been set to 0 yet by our DFS, then we're going to increment num islands, because that's the start of an island. And then we like clear all of the land there. Like we make all of them into 0s, because we don't want to count it again in the future. And then if we see a 1 in the future, it wasn't part of an island we've already seen, because we've already went to 0. So basically, this just counts the number of islands. And this DFS, yeah, as I mentioned, this just makes sure that we don't go out of bounds, but otherwise, it just visits the neighbors, and that's it. And so hopefully that made sense. Hopefully that was kind of instructive, and so you get something out of it. Because like this kind of problem is a good problem to know how to solve, for sure, especially if you're doing technical interviews or things. So I think that's about it. Yeah, questions about anything? Of course, you can always message me, and extra resources are here. So thank you all so much for listening, and yeah, have a nice day. Bye.